Yeah. This is the continuation of structural analysis class. Uh, so, in our discussion, we are discussing about a calculation of normal thrust and radial shear. So, we have the formula for normal thrust, that is equal to h cos theta plus v sin theta, and then radial shear equal to h sin theta. Pranati, put it in mute mode. Yeah, thank you. And radial shear, it is h sin theta minus v cos theta. And calculation of theta, I have already said, that is tan theta equal to, we have the equation that is 0.8 minus 0.054 x, which is one time differentiated this y equation with respect to x. So if we substitute for the value of x over here and theta equal to tan inverse of that value, we are going to get theta value. And x over here in question, you can have a look. We are asked to calculate the normal thrust and radial shear. Okay, normal thrust and radial shear at a distance of 9 meter from left hand support. So we need to substitute the value of x as 9 meters. So here it is substituted value of 9 as x as 9 meter. So theta you are going to get it as 17.43 degree. And V is the shear force. Shear force at a distance of 9 meter in the given arch. So if we have a look on this, VA towards up and up to 9 meter you come for. UDL is acting towards down. Deduct the value of VA by the load which is acting towards down. That is 9 9 into 30 kilonewton per meter, multiply it, so that is the value of shear force. That is what it is calculated over here. VA minus 30 into 9, value of VA is 355.5 minus 270, so that shear force you will get 85.5 kilonewton. And the horizontal reaction, that is H value, already it was calculated, that is 326.25. If you substitute all these values, 326.25, 17.43 and 85.5, we'll get normal thrust value 336.88 kilonewton and a radial shear value of 16.15 kilonewton. And this was already explained, the calculation of bending moment at a distance of 9 meter from left hand support. So that's all about calculation of normal thrust, radial shear and bending moment. And now how to draw bending moment diagram. See, at mid-span of AC, we had calculated the moment value was 360.5 kilonewton meter, which was sagging in nature. And when we calculated moment value, bending moment value at D, we got that value as MD equal to minus 245 kilonewton meter, which is hogging. Okay, so hogging will show below arch and sagging will show above the arch. So at point A, B, and this crown C, we know that bending moment value is 0. So we start with 0. As the load is acting uniformly distributed load on left half portion of the arch, the variation of bending moment is parabolic in nature and which reaches 360.5 kilonewton meter. And then from there again parabolic variation which will reach the crown point where the bending moment value is 0. And then from this crown point till this 60 kilonewton point load, it is linear in nature, and from there again to the support B, it is linear in nature, which is hogging. Okay, so this is the point where 60 kilonewton is acting. So from here till here, 60 kilonewton towards down will come straight and then will connect it to support B. And the value of that bending moment is 245 kilonewton meter. So this is how to draw bending moment diagram for the same. So another example where horizontal component of force also which will come, where two inclined forces are acting on the arch, and the span of arch it is shown in the figure itself, that is 20 meter, and the 150 kilonewton force at an angle of 45 degrees is acting at a distance of 5 meter from left hand support, and 200 kilonewton at an angle of 30 degree is acting at a distance of 6 meter from right hand support. So for the three hinged parabolic arch shown in figure, we have to calculate the support reactions, and also we need to determine the maximum bending moment in this arch. The question is simple. They have not asked to determine radial shear and normal thrust. Only we need to calculate maximum bending moment and support reaction at the same. So we have conditions of equilibrium. So summation of Fx, summation of Fy, and summation of M equal to 0. So before that, we'll start with a rise equation, that is y equal to 4 times of h divided by L square into x into L minus x. And h, it is substituted 4 meter, which is given in the question statement itself, that is 4 meter. We substituted 4 times of h divided by L square. L is 20 meters, so 20 square into x into L minus x, where L is 20. Okay, if we substitute the same, we'll get this equation. And then, yeah, so the vertical ordinate height at D and vertical ordinate height at E, if you want to calculate, you can substitute the value of x ordinate, that is 5 meter, from left side for calculation of YD. So for that, you will get 4 4 is 16 divided by L square, that is 20 square, into x, we are substituting it as 5 meter from left side, 5 into L minus x, that is 20 minus 5. So vertical ordinate height at point D, it is 3 meter. And in the same manner at E, the distance of point E from the right hand support, it is 6 meters. So 6x value will be substituting it as 6. So we'll get 3.36 meters. The vertical ordinates height at D and E we have calculated. For finding out a support reaction, apply first condition of equilibrium, assumption of all the vertical forces equal to 0. Vertical reaction at A, vertical reaction at B equal to 0, minus the vertical component of 150 kilonewton is 150 sine 45, and vertical component of 200 kilonewton is 200 sine 30. So both components it is substituted here, so that we'll get equation VA plus VB equal to 206.06. That is equation 1. And a summation of horizontal forces we can use. Before that, the moment equation we have used over here. So that is summation of moment about A equal to 0. If we take VA and HA will not produce any moment over here. So 150 sine 45, 150 cos 45, 150 sine 45 into 5 meter, trying to rotate in clockwise direction positive, 150 cos 45, and vertical ordinate height, that is YD already calculated, that is 3 meter, trying to rotate in clockwise direction, that is also positive. And about the same point, when it comes to components of 200 kilonewton, 200 cos 30 and vertical ordinate height, that is YE, that is 3.36 meters, and trying to rotate in anti-clockwise direction negative. And then vertical vertical component of 200 kilonewton, that is 200 sine 30, and perpendicular distance is, it is 10 plus 10 minus 6, that is 4, totally 14 meter from here, trying to rotate in clockwise positive. And then VB and perpendicular distance is 20 meter, trying to rotate in anti-clockwise, minus 20 times of VB. If we do so, we are going to get the value of VB. So that is what it is done. Summation of MA equal to 0. We got VB equal to 83.32 kilonewton. And substitute this value in equation 1, so that VA equal to 206.06 minus 83.32. We'll get value of VA as 122.73 kilonewton. Okay, so the vertical reactions we are done with, and the horizontal reaction, that is H value, we need to determine. For the calculation of H value, we can take moment about this ground, that is C equal to 0. So that take moment of or horizontal and vertical component of 150. And any one side we can take over here, H into 4 and VA into 10. So if we take this, we'll get value of H. So see here, 200 sine 30 into 4 meter positive clockwise, and 200 cos 30 into perpendicular distance is 4 minus 3.36, and then minus 83.32 into 10 plus h into 4, where here we have taken the right half portion. So vertical and horizontal component of 200 kilonewton, and then vertical reaction, that is at VB, and then h into 4. We substitute, we'll get 80.59. Okay, and then a resultant component of V and H, that is a VA and H. RA will be equal to root of VA square plus H square, and RB will be equal to root of VB square plus H square. If we do so, we'll get the resultant component or resultant reaction at A and resultant reaction at B. So RA and RB, it is done. And theta A and theta B, the direction of RA and RB we have calculated here. That is theta A equal to tan inverse of VA divided by H, and theta B equal to tan inverse of VB divided by H. Okay, if we do that, we'll get 56.7 degree and then 45.95 degree. So first question, that is a support reaction. It is done, that calculation. Now you come for the calculation of bending moment. So bending moment in question, if you see, determine the maximum bending moment in the arch. Okay, whether it will happen, where exactly it will happen also, we can determine. So moment at D will start with. So moment at D, any one side we can take. So 122.73. Let us have a look. 122.73, that is VA. So one side they have taken this side. So VA into 5 meter. So that will rotating clockwise positive, and H into YD, that is 3 meter. Trying to rotate in anti-clockwise direction, negative. So the value of moment at D is 122.73 into 5 minus 80.59 into 80.59, which is nothing but H into 3. So we'll get 371.88 kilonewton meter. That is moment at D. So if you go for calculating moment at E, so moment at E, if you can take, you can consider any one side portion, that is the right portion it is considered here. So VB into perpendicular distance is 6 meter, trying to rotate in anti-clockwise direction, negative. And then H into perpendicular distance is YE, that is 3.36 meter, which was calculated. So that will rotate in anti-clockwise direction, negative. So if we do this calculation, you will get 229.13 kilonewton meter. So maximum among these two, that is 371.88 kilonewton meter. So this is the maximum bending moment. Okay. So by using conditions of equilibrium, we are analyzing these 3-hinged arches, which is statically determinate. Okay. So we are done with the analysis of arches. So in the same support at different level also, you can go for. Now you come for next topic, that is analysis of cables. So different components in the cables, you can have a look over here. So this is the suspension cable, which carries this road or deck slab, and then which are continued. This suspension cable is continued as anchor cable, and which is fixed to a point on the earth. And then these are the towers which will support this cable, which will run on. Okay. And then for the analysis purpose, you can take a uniformly distributed load which will be acting on this deck slab, and which is supported on this cable, and distance from the horizontal line drawn from support ends to the lowest point of this cable is termed as dip. Okay. So when it comes to the analysis of cable, we may have to determine the tension force which is there in cable, and in this maximum tension force and minimum tension force will be determining. So maximum tension force is root of V square plus H square. So where V is the maximum vertical reaction and H is the horizontal reaction. So at this portion where exactly the tower is placed, over there will determine the horizontal reaction force and vertical reaction force. Okay, the direction of H, you can have a look over here. It is away from this cable, as the cable will pull inside, and this resultant of V and H, that will be root of VA square plus H square, and resultant of VB and H is root of VB square plus H square. So which is maximum among these two? That is the maximum tension force which is experienced by this cable. And then minimum tension force, normally it will be there at the lowest portion of this cable, that is at point C. So that minimum tension force, which is nothing but the horizontal force, that is H. There will be no vertical component at the lowest point of the cable. So minimum tension force will be equal to H, that is horizontal force, which exists at the lowest point of the cable. So these two formulas you need to remember: maximum tension force and minimum tension force in the cables, root of V square plus H square and H. And how to decide the size of cable when it comes to design part. So that we know that stress is equal to force divided by cross sectional area. So if it is mentioned the cable should not be stressed beyond certain limit or permissible limit, if it is specified, then we know the maximum tension force, that is nothing but the force we can substitute here, and permissible stress we can place it here. So that area will be equal to force divided by stress. So that is the cross sectional area we get. And then if circular cable like cross section we are using, means pi d square by 4 can be substituted at the place of area of cable, so that we are going to get the diameter of the cable. And then if we need to calculate the length of cable by looking at the geometry, so if the supports are at same level at both the ends, this is the formula we use, that is S equal to L plus 8 by 3 into D square divided by L. You need to remember this. And then if the supports are at a different level, another formula, that is S equal to L plus 2 by 3 into D1 square by L1 plus D2 square by L2. You can have a look on this sketch. D1 is dip, okay, the lowest or bottommost point of the cable to the location of support, that is D1, and D2 is another support level to the depth, D1 and D2, and L1 and L2 is the horizontal distance from the support to the lowest point of the cable, okay, L1 and L2. And then the forces which are coming on the tower, if you want to calculate, so in that two conditions will come: cables passes over a smooth pulley and cable connected to a saddle or roller. So first condition, if the cable passes over a smooth pulley like this, okay, the tension force in the cable is same as tension force in the anchor cable, okay. And the direction of anchor cable which can be fixed, okay, it depends on the site scenario. And then direction of this cable can be calculated by looking at the value of V and H, okay. This is the height of tower. The net horizontal force formula is T cos theta S minus T cos theta A. You can resolve this. So horizontal component of this T is T cos theta S, and horizontal component of this T is T cos theta A. So T cos theta A is towards left, that is by negative. T cos theta S is towards right, so that is by positive. So net horizontal force is T cos theta S minus T cos theta A. And vertical force is the vertical component of T both the side. Okay, this is T sine theta S, this is T sine theta A. Both are towards down negative. If you send another side, it will become positive both the side. And moment at the bottom of tower, if you want to calculate the net horizontal force, what you have calculated, multiplied that with the height of tower. Okay. So this is how to calculate net horizontal force and vertical force and moment at the bottom of tower when the cable passes over a smooth pulley. So when the cable connected to a saddle or roller, in that case, the tension force in the anchor will not be same as tension force which is there in the suspension cable. That is different. So we need to calculate that. We know the direction of a suspension cable. We know the direction of a anchor cable. So in this case, the net horizontal force will be equal to zero. This is the known thing. So that we can equate T cos theta S to TA cos theta A. If we equate it, the value of T will be known, theta S will be known, theta A will be known, so that theta A can be calculated. And then net vertical force will be T sine theta S plus TA sine theta A. And moment at the bottom of tower will be zero because the net horizontal force will be equal to zero. So this are all the list of formulas you need to remember and also the concept. Now you come for one sample or example problem on the cables. So you can read this problem. A suspension bridge of 120-meter span has a central dip of 12 meter. So the value of D is 12 meter and value of EL is 120 meter and supports a UDL of intensity 15 kilonewton per meter throughout the span. So UDL intensity 15 kilonewton per meter. So we need to calculate the minimum and maximum tension force, T minimum, T maximum. So T minimum is equal to H and T maximum will be equal to root of V square plus H square. The size of the cable if the permissible stress of the cable material is 200 Newton per mm square. We know the formula for stress equal to force by area, where force is nothing but a maximum tension force. So area you can equate it to maximum tension force divided by permissible stress, that is 200 Newton per mm square. So the diameter of the cable can be calculated. And then length of the cable. So a particular case is mentioned means directly we can go for using a particular formula, whether the cable is running over a smooth pulley or a saddle or roller. Okay, so you come for the solution. This is the diagrammatic representation of given data in the question. The span of this cable is 120 meter and dip is 12 meter, and vertical reaction and horizontal reaction free body diagram it is written over here. So for calculation of VA and H, VB and H, we can use the conditions of equilibrium, summation of all vertical forces equal to 0. That means VA and VB towards up minus 15 kilonewton per meter is the intensity into 120 meter. So that will be VA plus VB equal to 1800 kilonewton is the equation we'll get. And then you can take moment about any one support over here. So moment about A equal to 0, it is taken here. So moment about A equal to 0 means 15 into 120, which will, that concentrated load will act at center at a distance of 60 meter from left hand support. So 15 into 120 into 120 by 2 is 60, which will rotate in clockwise direction with respect to A. So that is positive, 15 into 60 into 60 by 2. And then VB into over here, and then VB into 120, VB towards up into 120 meter is the distance. And H, if you extend the line of action, it will pass through A. So there is no rotation or moment. So if you equate it to 0, you will get a VB value as a 900 kilonewton, 900 kilonewton. Substitute this value in this equation, you will get a VA value as 900 kilonewton. So done with the value of V and VB. So now for the calculation of H, in case of arches, we need to go for taking the moment at crown. So here you can take a moment at midpoint C. And if you take moment at any point in this cable, that moment value will be equal to 0. In case of arches, moment value at only the crown used to be 0. At other location, moment used to be there. But where in case of cables, moment at any point over the cable, it is 0. Rather than taking moment at C, you can take moment at any distance over here so that you will get value of H. So summation of moment at C equal to 0. If you take VA into perpendicular distance is 60, trying to rotate in clockwise direction positive. H into perpendicular distance is 12 meter, trying to rotate in anti-clockwise direction. So that is minus. And then if you take this 15 kilonewton per meter into span is 60, 15 into 60, which will act at 60 by 2, trying to rotate in anti-clockwise direction negative. But where in case of this, it is taken for right hand side from point C. So 15 into 60 into 60 by 2. So that is for this portion, trying to rotate in clockwise positive. And then 900, that is nothing but VB, trying to rotate in anti-clockwise direction with respect to C, that is minus 900 into 60, plus H into 12, trying to rotate in clockwise, that is positive. So the value of H, that horizontal reaction, it is 2250 kilonewton. So value of H is done, value of VA and value of VB it is done. So the maximum tension force is root of V square plus H square. So out of these two, both are same value. so that both are having maximum values. We can substitute value of V as 900 square, and then 900, and the value of H as 2250. Here in this formula, square is required. So 900 square and 2250 square, maximum tension force is 2423.32 kilonewton. And minimum tension force, which is nothing but the horizontal force, that is T minimum, will be equal to 2250 kilonewton. Okay, if you compare 2250 and 2423.32, 2423.32 is maximum, so that is the maximum tension force. So now other questions, that is the size of the cable and length of the cable. So when it comes to size of the cable, we have the formula for stress equal to force divided by cross sectional area. So that cross sectional area will be equal to that stress, that maximum tension force divided by stress. So that we'll get the diameter of the cable, that is 124.20 mm. You can round it up to 125 mm diameter of the cable is required to carry the maximum tension force 2423.32 kilonewton. And the next question, that is length of the cable need to be determined. Supports are at the same level, so that formula is S equal to L plus 8 divided by 3 into D square divided by L. Value of L span is 120, and then dip value is 12. So that you just substitute the values, you will get 123.2 meters. So this is how to calculate the length of cable. So whatever it was asked over here, that is minimum and maximum tension force, size of the cable and length of the cable, it is done. So beyond this, if you want to calculate the forces which are coming on the uh, supports, okay, or the tower. So over there, two conditions are there: cable passes over a smooth pulley and cable passes over a saddle. If you take cable passes over a smooth pulley, so tension force both the side it is same, and it depends on like the matrix, the direction of this anchor cable. So in the problem it was not mentioned. If it is mentioned like a 25 degree, if you consider, so theta a you take it as 25 degree, and theta s it is to be determined. That is value of V and H already determined. So that theta s equal to tan inverse of 900 divided by 2250. So that you will get 21.8 degree. And maximum tension force both the side it is same. And height of this tower we have considered it as a 20 meter. If in question if it is mentioned, so accordingly you need to take the value. So net horizontal force will be equal to 2423.32 cos 21.80. That is horizontal component resolved part. Okay, 2423.32 cos 21.8 positive, and then 2423.32, that is towards left, minus into cos theta a, that is cos theta a is 25. Okay, minus 2423.32 into cos 25. To substitute this, you will get 53.74 as the net horizontal force. If you multiply this 53.74 net horizontal force with the vertical distance at 20 meter, you will get moment about the base. And the vertical force, if you want, you just take the vertical component, that is 2423.32 into sine 21.80 plus 2423.32 into sine 25 degree. Add both, you will get the vertical component or vertical force, that is 1924.08 kilonewton. So this is how to calculate net horizontal force, vertical force, and moment about the base of the tower. And if the cable passes over a saddle, you just have one condition, that is T cos theta S, horizontal component of this equal to horizontal component of this. T cos theta S equal to TA cos theta A. So value of T you know, theta S you know, theta A you know. You just substitute, you will get theta tension force in the anchor cable as 2482.62 kilonewton. Okay, and then if you want vertical force, you just resolve this TA T so that 1949.14 kilonewton, that vertical force you are going to get. So one sample problem on analysis of cables which is subjected to uniformly distributed load I showed. So cables may be subjected to concentrated load sometimes. And another example on the same topic, So in this problem, we need to determine the tension force in the various segments of the cables, and also we need to determine the diameter of the cable required if the allowable stress in the cable is 150 Newton per mm square. See this cable A, B, C, D, and the direction of CD, CA, and DB, it is not given here. We need to calculate by looking at the geometry. And free body diagram, it is written as both the ends are hinged, VA and H, VB and H. Okay. So first, the calculation of directions. So here the value of y it is not given. We need to calculate that. But this one it is given 4 meter. So as this is 4 meter, it is given and 10 meter is given. The direction of CA can be calculated. So we can name it as theta 1. So this is also theta 1. So theta 1 equal to tan theta 1 if you take opposite by adjacent, that is 4 by 10. Theta 1 you will get 21.8 degree. And then theta 2 for the calculation of theta 2. So already calculated value it is shown here or here. So that is 4 minus 3.2. That 3.2 is nothing but the value of y. I'll show how we got the value of y as 3.2 meters later. So however you take this value of y as 3.2 meters, so that this is 4 meter means 4 minus 3.2 will give you this height. So that tan theta 2 equal to 0.8 meter divided by 10 meter, so that you will get theta 2 value as 4.57 degree. And then value of theta 3, value of y we know that is 3.2 meters divided by 10. So tan inverse of 3.2 by 10, you will get theta 3 value 17.74 degree. Okay. So over here it is shown how we got the value of y as 3.2 meters after determining the support reactions. So first you come for calculation of support reaction, summation of Fy equal to 0, so that V and VB towards up equal to 200 over here, 100 over here. Totally 300 kilonewton towards down, that is 300, equation 1. And if you take a moment about A equal to 0, 200 into 10 meter clockwise positive, 100 into 20 meter clockwise positive, VB into 30 meter anti-clockwise negative. So here it is written minus 30 into VB plus 20, 200 into 10 plus 100 into 20 will be equal to 0. So that VB value is 133.33. Substitute this value over here, you will get VA value as 166.67 kilonewton. So vertical reactions it is done. Horizontal reaction we need to calculate. Take a moment about C equal to 0. If you take moment about C, any one side you take, that is VA into 10 clockwise positive, H into 4 anti-clockwise negative. So substitute the value of VA, so that value of H will get, that is 416.67 kilonewton. So after determining the support reactions, so now you come for the calculation of this dip. So dip at point D. So how much is the dip at D we need to calculate. So for that purpose, you take moment at D equal to 0. Any one side portion you take, moment at D equal to 0 means VB into 10, trying to rotate in anti-clockwise negative, H into YD, H into YD, so that is rotating in clockwise positive. Okay, value of H we know, value of VB we know, so that YD we are going to get it as 3.2 meter. So after determining this 3.2 meter, we need to calculate this theta 1, theta 2, theta 3. So already I explained how to calculate that theta 1, theta 2 and theta 3. Now you come for calculation of member forces in different segments of the cable. At joint C, if you take, draw the free body diagram at joint C. So tension force means away from the joint, and here also away from the joint, 200 kilonewton towards down. Direction of CA you know, direction of CD you know, and then okay. So free body diagram, have a look. 21.8 degree, 4.57 degree, and 180 minus theta 1 and theta 2 will gives you 153.63 degree. And you can apply Lamis theorem for this. What Lamis theorem says? The ratio of magnitude of force when it is applicable for a three concurrent force system. in this, the magnitude of force in one direction to the sine of angle between other two forces. So those are all proportional to each other. So 200 towards down divided by sine of 153.63 is equal to TCA divided by sine of 90 plus 4.57, that is 94.57 degree, equal to TCD divided by sine of 90 plus 21.8, that is 111.8 degree. So at one time you take two components, 200 divided by sine of 153.63 equal to TCA divided by sine of 94.57 degree. You just cross multiply it, you will get TCA value 448.85 kilonewton. And you take this and this components second time. So that cross multiplication of 200 and sine of 111.8 divided by sine of 153.63 will gives you 418.08 kilonewton. So in the same manner, you can go for drawing the free body diagram at joint D. Again, you apply the Lami's theorem. You will get TDC and TDB as 418.03 and 437.5 kilonewton. Okay. So this is all about the analysis of cables. Two sample problems also I have showed over here. Okay. Next, you come for displacement method of analysis. That is a slope deflection method we'll discuss about. So this comes under analysis of indeterminate structure, statically indeterminate structures. So in this, we'll use compatibility conditions, which can be termed as conditions of equilibriums only. So one sample beam is taken over here, and the basic equation over here used for the calculation of moments. In this, if you take AB, this AB, that beam segment, the basic equation is MAB equal to 2EI by L into 2 theta A plus theta B minus 3 times of delta by L plus MFAB. So this MFAB is a fixed end moments. So those formulas you need to remember. Derivation is there, but it is good to remember the formulas directly. MFAB and plus E and I value. Uh, if it is given, you can substitute or directly you can maintain as per the given data. 2 theta A rotation at A plus theta B rotation at B plus 3 times of del by L, where del is the sinking or settlement and L is the span of beam. So that is moment at A with respect to B, that is MAB. Moment at B with respect to A, that is MBA equal to 2A by L into 2 theta B plus theta A minus 3 delta by L plus MFBA. Okay, you just observe over here in case of MAB, for theta A it is 2 times, and in case of MBA for theta B it is 2 times. Okay, these two basic equation you need to remember, and then fixed end moments for different cases you will have to remember. So fixed end moments when a fixed beam which is subjected to uniformly distributed load, fixed end moment MFAB is WL square by 12, and that moment fixed end moment in anticlockwise direction, so that sign convention is minus. MFAB is minus WL square by 12, and MFBA it is acting in clockwise direction, so that is positive, plus WL by 12. So when the beam is subjected to a point load at mid span like this, fixed end moment MFAB will be minus WL by 8, MFBA is WL by 8. So if it is not acting at exactly mid-span, somewhere in between means, so at a distance of A from left hand and B from right hand support means, MFAB is minus WAB square by L square, and MFBA is WA square B divided by L. If only moment is acting at mid-span or anywhere means, MFAB is plus M by 4 and also MFBA is plus M by 4, because the given moment is clockwise. If the given moment is anti-clockwise, that is minus M divided by 4. So like that for other cases also. So you can have a look and you need to remember all these cases. So these are all the fixed end moments. And now you come for the conditions of equilibrium or compatibility condition. See here, equilibrium condition. If we take A, B, C, D, CD is overhanging portion, A is fixed support, B is intermediate support. So at intermediate support, the sum of moment will be equal to 0. Over here, B is a intermediate support and C is a intermediate support. So at B, MBA plus MBC, the net moment over here will be equal to 0. And when it comes to the support C, MCB and MCD, you add, the net moment will be equal to 0. So when you call a support as an intermediate support, if you consider this sketch, A is not an intermediate support, it is an end support. So B is an end support over here and C is an end support over here. And which is the last support in this beam? So A is the last support, C is the last support, and B is the intermediate support. So the net moment over here, it will be equal to 0. Okay. So one sample problem, how to solve analyze the beams by using a slope deflection method. Problem statement you can read. Analyze the continuous beam shown in figure by using slope deflection method and draw bending moment diagram, shear force diagram, and elastic curve. So this is the beam. So at A it is fixed support, at B it is simple support, at C it is roller support, and at D it is again fixed support. So if you see this beam, you can say uh, support A and support D are the end supports, and support B and support C are intermediate support. So the net moment at B and net moment at C will be equal to 0. That is MBA plus MBC will be equal to 0, and MCB plus MCD will be equal to 0. However, moment will be there at A and moment will be there at D. And force acting on this beam is 50 kilonewton at midspan between AB, 115 kilonewton per meter throughout the length of BC, and 80 kilonewton at a distance of 2 meters from support C. And EI is constant, it is given here. If EI is different for different beam means, you will have to consider that EI in the respective equations, the basic equation, what normally you write. And fixed end moments, you come for the calculation of fixed end moments. So if you take only the segment AB, okay, the fixed end moment over here, it is that MFAB and MFBA is minus WL by 8 and plus WL by 8. The value of W is 50 and L is 4. If you have a look on this beam, you will get to know. So it is minus 25 kilonewton meter and plus 25 kilonewton meter. And then next beam you come for, that is BC, which is subjected to uniformly distributed load, and span is 5 and 15 kilonewton per meter. So that is the WL square by 8 minus and plus. So minus 15 into 5 square divided by 12. So the same value with positive sign convention, minus 31.25 and plus 31.25 kilonewton meter. And then when it comes to third span, that is CD, so at a distance of 2 meter from C, it is subjected to, that is minus WAB square by L square and plus WA square B divided by L square. So if you substitute, you will get minus 71.11 kilonewton meter and 35.56 kilonewton meter. So we are done with the calculation of fixed end moments. So now we need to calculate the actual moments which will act at different segment of the beam. So for that, we have few known things in this beam. Theta A equal to 0 and theta D equal to 0, and there is no sinking in the beam. So the delta part can be removed directly because there is no sinking. Theta A and theta D equal to 0, right? Why? Why it is 0? Because those two are fixed support. So this A and D both are fixed support. So there is no rotation at these points. But however, there will be certain rotation at B and C that we need to determine. The basic equation we have, that is MAB equal to 2A by L into 2 theta A plus theta B minus A delta by L plus MFAB. MFAB already calculated here, that is minus 25. So minus 25 can be substituted. delta part directly removed, there is no sinking, and theta b as it is plus 2 theta a, where theta a is 0 because it is a fixed, and 2 ei by L, where L is 4. So if you simplify this, you will get 0.5 ei theta b minus 25, that is equation 1. And MBA, okay, in the same manner MBA if you take, that is MFBA. MFBA is plus 25, and in place of a theta b we should write 2. 2 theta b plus theta a minus 3 delta by L. So 2 theta b and theta a is 0, delta is 0. We'll get equation 2. In the same manner, if we apply this basic equation, okay, for all other spans, we'll get equations MAB, MBA, MBC, MCB, and then MCD and MDC. Okay, so totally 6 equations we'll get. After getting 6 equations, we can apply the compatibility condition or equilibrium condition at intermediate support. So here the intermediate support, that is B and C. At B, you can apply MBA plus MBC equal to 0. You just have a look on which are all the unknowns at MBA and MBC. See here, MBA, that is EI into theta B plus 25. Theta B is the unknown. And MBC, theta B and theta C are the unknown. So in this equation, 1 is unknown. In this equation, 2 are unknown. Okay. So apply that condition of equilibrium. So MBA plus MBC equal to 0. You will get this equation in terms of theta B and theta C are as unknowns. You can call this as equation 7, or Roman number 1 is shown over here. And same compatibility condition at joint C also you can apply, that is MCB and MCD equal to 0. So MCD and MCB, you see here, at MCB, theta C and theta B are the unknown. MCD, theta C is the unknown. Okay, so that finally you will get another equation in terms of theta B and theta C. So this equation 1 and equation 2, you have a look. Theta B and theta C are the unknowns. If you solve these two equations, you are going to get the value of theta C and value of theta B. It is minus 2.73 and plus 27.91 divided by EI respectively. Substitute the value of theta C and theta B in these equations. Okay, so here you just substitute the value of theta B, you will get MAB. Here you substitute the value of theta B, you will get MBA. So like that, keep substituting the value of theta B and theta C. You will get MBC, MCB, MCD, and MDC. So this is where it is calculated. MAB, that is negative, so that it is anti-clockwise. MBA, it is 22.27 positive clockwise. Okay, so MCB clockwise, MCD anti-clockwise, MDC clockwise, and MBC anti-clockwise based on sign convention. It is shown on tab. Okay, so you can observe the value of MBA and MBC. This is plus 22.27. This is minus 22.27. So based on compatibility condition, you know that addition of both, the net moment will be equal to 0. In the same manner, it is MCB and MCD, you can have a look, the same value with other sign conventions. So the net moment value at that point is 0. Okay. So the shear force and bending moment diagram for the same, you can write. So this is the shear force and bending moment diagram. Okay. So in the strength of material session, we have already discussed how to draw shear force and bending moment diagram. Next, you come for some other type of structure, that is a frame, that is non-sway frame. There is no sway. Okay. A, B, C, and D. A and D are fixed support. C is a roller support. Okay. So at A and D, the known things are there is no rotation. Theta A and theta D equal to 0 directly we can say. And moment at C equal to 0 also we can say. And at intermediate joint at B, that compatibility condition can be used. So we have to analyze this frame by using slope deflection method, and we need to draw BMD, SFT, and elastic curve. So fixed end moments will start to calculate. We know the formulas for UDL, point load and all. So for AB, it is WL square by 12 minus and plus based on AB and BA, MFAB and MFBA. And when you come for BC, it is WAB square divided by L square. So from this side it is minus and from this side it is positive. And then this vertical member, you can rotate it and write it as horizontal, 2 meter, 2 meter. It is WL by 8. DB is negative and BD is positive. MFDB and MFBD. So it is rotated in this manner. So fixed end moment calculation, it is like this. You can have a look. After the calculation of fixed end moments, the known things are listed here. Theta A and theta D are 0 and there is no sinking. So delta equal to 0. It is shown here. MAB, MBA, MBC. So 2A by L into 2 theta A plus theta B minus 3 delta by L plus MFAB. That basic equation is used here. And as theta A equal to 0, it is not written. Directly it is written theta B. So that equation 1 will get. In the same manner, MBA will get equation 2. And MBC again between B and C will get equation 3. MCB, MBD and MDB. So up to 6 equations we got. Now you apply the compatibility condition or equilibrium condition at joint B, MBA plus MBC plus MBD equal to 0. So if we apply this, so MBA equation we have, MBC equation we have, MBD equation we have. So we'll get equation 2.8 EI theta B plus 0.4 EI theta C equal to minus 7.87 as equation 1. You can have a look the unknowns. Here also it is theta B is unknown, one unknown, this MBD. And when it comes to MBC, theta B and theta C are unknown. And when it comes to MBA, theta B is unknown. So totally two unknowns are there. So that finally we'll get the equation in terms of two unknowns. And then at C, because at C it is a roller support, right? So the moment at CB, moment at that roller support, it is 0. So that we can write MCB equal to 0. So MCB equation we have here, MCB is 0.8 EI theta C plus 0.4 EI theta B plus 9.2. So this will become another equation where B and theta B and theta C are the unknowns. Solve these two equations, that is Roman number 2 and Roman number 1, which is written here. Okay, we will get theta B and theta C as 0.67 E divided by EI and minus 24.33 divided by EI respectively. Substitute these values in the main equation which we got over here, so that we'll get MAB, MBA, MBC, MCB, MBD and MDB. Listed, and you can draw bending moment shear force diagram for the same. This is the bending moment diagram and elastic curve also it is shown over here. Okay, so that is another problem, an example for slope deflection method, that is non-sway train. Next topic is moment distribution method. Another method for the analysis of indeterminate structure. It is an iteration process we use over here. And you need to have the value of relative stiffness here. Two types of stiffness you have, absolute and relative stiffness. We'll use a relative stiffness for the calculation, that is K equal to I divided by L, where I is the moment of inertia and L is the span of the beam. Okay. And different support conditions will come, that is a fixed support, simple support, roller support, hinge support and overhanging portion, all are shown in this case. And the relative stiffness value, if the far end of the point of consideration is fixed end or if it is continuous. In such cases, the relative stiffness is equal to I divided by L. From the point of consideration, if the far end of the beam is fixed end or if it is continuous, The relative stiffness is K equal to I by L. If the far end is a simple or hinged support or roller support, the relative stiffness is 3 into I divided by 4L. If the far end is overhanging portion, then the relative stiffness value is 0, no stiffness at all. Okay, you need to remember these formulas: I by L, 3I by 4L, and 0. Okay, one example it is shown here. There is a continuous beam A, B, C, D. Okay, so with respect to B, if you come for, the far end is A, and A is not continuous. So the relative stiffness over here, it is 3 into I divided by 4L. And from